What do you do when a worker fails when it's pulling critical data? Two outcomes. That means the whole workflow could restart from scratch, or your system would have expected this failure. Sedai as a company, we deal with billions of data points every minute. Get the data, build our models, and that's how we operate. So your system has to understand that these failures could happen and it has to gracefully recover. And the brain behind this whole thing is with me today, Hari Chandrasekhar, one of my close friends in life. I'm Suresh Matthew, and this is One Idea. You're welcome, Hari, to this show.
Thank you, Suresh. Thank you for having me.
So, Hari, for us, it is clear that these large, very, very large enterprises, they rely on your data collection for the next action. So there is no excuse that there was a failure and you were innocent. That doesn't fly. When there is a failure, you have to stand up and take the responsibility, which means now your system has to understand that this is what Sedai is doing, this is the mission, and this mission, incorrect behavior cannot be justified. They trust us with their business. How did you design that system?
So you're absolutely right, Suresh. The environment that Sedai works in requires connecting to a lot of external systems, be it cloud provider APIs or monitoring provider integrations. There are a lot of failure points. And on top of that, we are always running on cloud systems, and infra failures are also.
Meaning your infra is on cloud.
Correct.
Okay.
Yep. So we are dealing with cloud systems and we are running on cloud systems as well. So there are so many failure points. So it is hard for us to expect that our system will be running without any problems.
So you're expecting failures in between.
Absolutely.
In fact, it's the other way around. So your systems ideally are surprised when it runs smoothly. It should be the other way around. It should be shocked when a job completes on time.
That is absolutely correct. Yeah. So to begin with, our design itself in such a way that we accept failures. So we know that there could be so many failures happening. The system is designed in such a way that one or two failures is not going to create any impact. It's like a real world system, right? In real life, we know that there could be problems. Let's say we are taking a car to reach a certain point, there could be traffic jams. So we know that that could happen. So you try to account for those delays and see how we can work around it. It's not that because of a traffic jam, we stop and come back. We navigate around. That's how the system itself is designed. You don't try to make your system work perfectly all the time, because you're not the only system in the mix. You're talking to a bunch of systems, and failure is expected all the time.
You could be innocent in that failure too.
Another thing is, as we said, like we are also trying to run on cloud infrastructure. And of course, the cost is also a big factor. So we want to run on, or we want to reduce the infrastructure cost as well. That is also one of the goals, just like any other company. So we want to make sure that we are not unnecessarily using compute if we really don't need to do it. So there is also this optimization angle that also play into the design.
Got it. So there is a resource optimization side of like selfish motive. Let's put it that way. And there is the other aspect, which is reliability and performance. I'm thinking those two are coming together.
The approach is, when you write the system, of course, like any other software applications, there is always the failure path. Like how do you deal with it? The way we have done it is, it's always failure first. You fail, but the system in general doesn't need to do too much to say that, hey, it failed. Do I need to go into the panic mode? Absolutely not. Continuously do what you are trying to do. The system's design will make sure it covers for the previous failures. So we account for those kind of failures and try to tackle it going forward. It might mean that we might not act super fast.
Which is also a good thing to do when you don't have the data.
Absolutely. Being an autonomous system, that is also very critical. We don't want to act with partial data. We want to make sure that we have the full context before we act.
Tell me, what monitoring products do you support? Is it everything in the world, or is it a few selected ones?
We support a lot of them. So for example, when we talk to AWS, we use CloudWatch as a primary monitoring provider source. We have a lot of Kubernetes systems, so we connect to Prometheus compatible providers like Mimir, Victoria Metrics, Datadog. New Relic.
So basically all APMs, almost all APMs. So you get collect metrics from all these APMs. You pull that data in, and that's the feed into your model.
Our approach is, different systems have different ways of collecting data, different granularity. So we've built an abstraction layer which understand the nuances of each monitoring provider. For example, most of the APMs have some kind of a rate limiting built in. Some customers use their own hosted infrastructure, like Prometheus is a very common one, which is hosted by the customer. There we may not have exactly the same rate limiting problem, but we still have to account for, overusing their API. So we do have, some kind of an agreement with customers that we don't overload their system when you are trying to fetch the data. So there is always this constraints that we work with. At the same time, we are also trying to build that abstraction layer where our core systems can get the data in a very normalized fashion. And failure is also a critical component. As I said, like rate limiting is one of the factors which is outside of our control. Most of the times, what we have observed is um, we are not the only system which is pulling data from the monitoring systems.
Oh, so you have to work with those providers and make sure that you don't create problems with the current existing systems. So basically, when you had the system, it used to crash. And I'm talking about the system you had before. And these crashes were a little painful for you. You had to go back and fix things. Tell us, what was the impact of a crash? Was it data loss? Was it a wrong action?
Resiliency was built into the system. We've designed the system.
So wrong actions is out. That doesn't happen. Okay.
We will rather be more conservative and trying to assume things. The harder things were collecting metrics. This is usually where we see a lot more trouble than our actions itself. Of course, metrics are key to our algorithms. So our systems, all our components were already designed with resiliency and failure tolerance in mind, but it was baked into the application itself. For example, you're probably familiar with how Kubernetes controller works. There is a goal towards which the controllers are working. So one cycle miss, small hiccups is usually not a problem because you're still in that journey to achieve the goal. So Sedai's design can be thought in that fashion too. So it's one failure or one cycle misses usually doesn't create a problem. We try to catch up. But as I said, this whole design was built into the application itself. So each component took the responsibility. So they were independent, there were clean separation of concerns, but this design was built into the application itself. So in case of a failure, after all, it is still a constrained system. The system has all these things baked in, but sometimes, for example, rate limiting goes on for a while. There are other systems which are trying to utilize the metrics from the same source that we are collecting data from, and our quota is limited. So we can retry.
You
will
cannot fix it. Yeah.
Correct.
You have to live with it.
At that point of time, if you want to actually go fix those things, there needs to be a human intervention. And sometimes you come up with slightly better ideas of handling it, which requires these design changes. So what we decided to do was, instead of trying to actually put it into the system, why not share the responsibility? Instead of each individual components taking the responsibility, let's split it. Put more sensors out, more knobs out, which can be shared with the infrastructure system or the tools which are managing the infrastructure. So you get more flexibility at a runtime. So for example, we see this totally new pattern of failure in a particular customer environment because of the systems that we are integrating with. We don't need to maybe change our design for improving the reliability. We can see those extra knobs which are available at the runtime. Maybe this is a config or a resiliency mechanism that we have never used before, but you could tune that in the runtime using the insight that we are getting. So it's primarily shifting the responsibility from each individual components and exposing it more so that we can tweak more things at the runtime.
I hear you. So when you have missing data, right? So one option for you is to fill that missing data with some regressions, right? Let's keep it simple, right? So you can do a y equal to mx plus c on it and say, what, this is where it's going to go. Or you can do a curve fitting and say, what? Yes, let's fill the data. Do you do that at times or do you not?
And not assumptions, but metrics. If you're looking at the metrics, sometimes it is important for us to be super granular. Let's say when we are making autonomous actions, We want to make sure that we are not missing the spice.
So for actions, you will not rely on this data fillers. But for other things, for seasonality, you might rely on the fillers, which is the right thing. Okay, I see, I see. It depends on the use case. Okay, got it, clear. Now, when these failures happen, yes, there are a lot of conversations about how we can make things better. Yes, you could have done incremental changes. I'm sure we have made those attempts. And at one point, you decided, you know what? Let's let's go back to the whiteboard, right? Let's start drawing everything. And what was the trigger there?
Just like most of the modern systems, we started with smaller components with separation of concerns. But being a startup, we didn't want to actually explore too much. Having too many services, smaller services, had its own problem, the management, releases, and all. But there was this moment when we just realized that maybe this is the time where we need to actually go more granular. So there were two main reasons why we decided to do it at this point of time. So one was the point that I mentioned earlier. Said I wanted to actually utilize the learnings that its product is doing, because we know that there are a lot of fine tuning that we can do at runtime using all the signals. So we wanted to make sure that we share the responsibility. The other one was mainly driven by the current AI wave. Just like most companies, we are utilizing all the AI, generative AI systems, and of course we are using that in our dev and our operational cycles as well. So one thing that I think most of the people would have noticed is these AI systems work much better if you have clean context. It works very well in greenfield areas. If the context is smaller, the accuracy and the speed at which we are getting the results, the validations are much more effective.
MVP is quicker.
Exactly. But when you have the bigger projects dealing with more contents, even though it is not really a monolith, you get better results with smaller projects.
So you finally decided, yes, we have to change this. And you picked hub and spoke, and why?
We were extending the same philosophy of um, reliability and fault tolerance. So earlier, as I said, we had it in one individual single components, but now we are trying to layer it. We are, of course, moving into a more distributed architecture. So we have individual components which are executing certain things. There is an orchestration layer, and then there is this orchestrator itself. So what we wanted to do was, instead of relying on all these fault tolerance mechanisms in individual systems. So for example, we use messaging at this point of time for orchestrating the jobs. Of course, there are so many things you can use in that messaging layer to be tolerant, but we didn't want to actually just rely on one single system. So we have the concept of these jobs, or you can call it workers, which actually does the spoke things, which is basically the smaller job that it is supposed to execute. So it takes the responsibility at an application level. So for example, simple retries, those kind of things, exponential back off, those kind of things are baked into the application itself. So that is the first level of defense. And then there is um, mechanisms at the messaging layer to make sure these messages are delivered and acknowledged and responded to. But at the same time, we also wanted to make sure that there's one single custodian who is just overlooking everything.
So that's why you pick that architecture. There are failures where you lose the data. There are failures where your system is or the job itself is failing. There could be failures where the messages are not coming, right? So multiple types. I'm just calling it three. Do you respond similar to all three, or you respond differently to all three? All three.
At the end of the day, it's actually the goals.
Perfect. So it doesn't matter.
It doesn't matter, yeah. So as I said, like the multiple levels of resiliency that we have built in, but finally there is this
The end state.
correct. If we are actually trying to reach to that one, so there might be retries happening at multiple levels. At the end of the day, what we are trying to do here is, okay, did we achieve the goal? If not, what is the next thing that we need to do? Every layer is actually trying to get to that level.
So in our previous company, we called it something like Wispy and Wiry. And in this case, there are micro Wispies and micro Wiries. And every system knows where it has to take you. And the rest of the systems know what the state is. And they know how to transition. So failures don't become a problem. It becomes a behavior within the system. It's a different if condition in the flow.
You can put it that way.
Got it. And did you have to write the code from scratch, or design from scratch, or architect from scratch?
It's a mix of all three, yes. So if you think about the core logic, um, that remains the same. But how it orchestrates. So earlier, as I said, the individual components had the responsibility of making sure that it was fault tolerant. Now we are shifting that responsibility slightly outside. It's not that everyone is independent of the fault tolerance or the reliability in mind. It is there, but it's dealt with a different level at each layer. So, for example, the worker who is dealing with the actual job, the job is to make sure that the basic level of resiliency is maintained and report the status properly, so that we have an orchestrator who is well equipped with the decision making. Did I fail? Like, for example, an individual job might fail for multiple reasons. Of course, it'll do basic retries, and if it fails, it's not going to do exactly. It just says that, okay, I'm done. I did like 60% of the work. I'm calling it quits. Then it becomes the responsibility of the orchestrator to see, okay, now what should we do with this one? Do we still have value if we retry? Like, for example, we might be seeing a spike and the data is maybe like 30 minutes back.
Mm-hmm.
Now we got another fresh set of data, which is actually still
Why
giving.
bother? Yeah.
Exactly.
Exactly.
Yeah.
So you have to make those decisions at the hub.
That is right. Yep.
Okay. So the mothership decides, now that you have tried enough, just come back to me. You guys are all tired. Take it easy. I'll decide if you guys want to go back and do this again. And is it both done by or managed by the same set of developers, or do you have a team managing hub and a team managing spoke?
If you look at the design, right, we are trying to build this abstraction layer so that people who are focusing on the actual work don't need to worry about this resiliency part. So they follow a standard set of design principles. So somebody who's working on an exporter, they know that they need to report the status back, but they don't need to worry about at what point you need to
Exactly. So it
to make the
makes
news.
everybody's life easy.
Correct.
I'm assuming you're using Java. So you use your own like interfaces to define everything so everybody knows what the contract is.
That is correct. Yeah, we are primarily building it for Java components, but the design is in such a way that we'll extend it for all other programming languages too. So we pick different programming languages depending on the need. Like, for example, we have ML modules which are primarily using Python libraries. So Python was the default language of choice. And similarly, we have other components which are in Go. And so we didn't want to actually restrict this whole architecture to any specific programming language.
So you have, I'm thinking, almost all languages in play, 3 primary languages, and this is common for all 3. Now, the intelligence in the hub, I get the advantages here. Outside of this rate limiting is one fundamental use case. Outside of this, what are the other advantages one gets by adopting this design? What does let's say, a simple calculator app, what is the advantage of really getting this hub to make these decisions?
So the basic things like the separation of concerns and scaling. Scaling is another big factor which is helping us, here. So in the sense, as I said earlier, we have 2 goals in mind. Um, different applications, different customer environments have totally different scales. Sometimes you're dealing with a smaller set of applications that we are managing, but the amount of metrics that we are getting, the activities is super high. So you need to have that kind of um, uh, a scale for individual applications. So it is usually not just the amount of resources that you're dealing with, but there are so many different factors that impact your scaling needs. So with this architecture, what we are trying to achieve here is, first of all, we want to make sure that there is one single brain which is taking care of all the decisions. It knows when a particular job is required, whether it needs to be completed in time, there is a retry required. So that reliability part is
It's
completely
completely on this guy.
yeah. And at the same time, we also want infrastructure. So, for example, the core, the hub might come in and say, okay, I want these 10 things to be done. Now, do we have enough resources? Do we need like a scale? Like, for example, a particular customer environment might require like 100 different parts of a particular component to do the job, but it might be 200 for another customer, depending on the load that it is coming through. This architecture helps those kind of scaling decisions outside. So one is we can easily scale. We don't need to actually calculate all these resource requirement beforehand. We can do this completely at the runtime. And at the same time, we also have this cost angle in mind. Sometimes we deal with certain set of data that is not super critical. So we have, to give you an example, we have a concept called opportunity generation. So it kind of looks at the data and comes up with a very high level bird's eye view of what Sedai can achieve. That probably doesn't need to know each and every nuance of the metric that we are looking at. And it doesn't need to be reported like right now. It's not as time sensitive as a general operation. So we have built something like a priority queue. So the orchestrator calls that, hey, I need these 100 jobs. 20 of them is super important. The other 80,
It's okay.
yeah. We kind of leave that sensors outside so that we can actually control the knobs to say, yeah, if the medium jobs or the low priority jobs doesn't need to happen immediately, you have two things you can cover. So for example, the rate limiting, going back to that example, of course, even if you throw in like 100 different jobs to execute at the same time, you might be encountered with a rate limiting. So effectively, nobody is going to run fast. But at the same time, there is also cost associated with it. You could run the low priority jobs at a different time, without having to run all these things in parallel, and maybe even run it on a spot instance as well.
Oh, the whole thing.
The whole thing, yeah.
Okay.
With this new architecture, what we are trying to do is we are letting these jobs run on a spot instance because we are inherently fault tolerant.
That's a good proof, right? So if we can confidently run on spot, I do understand that we don't do that with everything, but if you're confident that you just need spot, that's a new clean level of architecture. It's not easy to achieve.
That is correct, yeah. One of the decision that we have made is these jobs, the components which are actually executing the jobs, are aware that they could be running on a disruptive environment. What it tries to do is it is actually constantly in the look for signals to say that there is going to be a disruption. And we have kept it super simple. You be aware that there could be a disruption. The only thing that you need to do is report the status correctly. In Spot, your application could be shutting down pretty quickly within like a 2 minutes notice or a 30-second notice, depending on the cloud provider. So the best thing you could do is wrap up what you're doing, send a status back saying, I've completed so and so, or if that particular job couldn't do anything, report the status and come out of it.
So Hari, we have to take failures and we have to now figure out, should we retry, should we do something else? What is the reason? Tell us more about why would you look deeper at a failure? Why are you so worried about taking an action then? Why can't you do that offline and probably add a support person and say, you know what, dude, there was a failure. Go check out, right? What is different here?
Let's take a simple example: opportunities.
What is an opportunity, by the way?
Opportunity is what Sedai thinks it can configure or reconfigure in customer's environment, which meets the customer's goal.
So basically, you are trying to change an application or change an application configuration so it runs faster,
correct,
or cheaper, or save some money, and that's an opportunity.
So when we are building opportunities, we are looking at larger set of data. We are looking at the application patterns over time to say, okay, what are the patterns we are seeing? What is the traffic rate it is getting? Or what are the spikes it is going through? And see what would be the best configuration.
So this is like tens of thousands of applications, getting all the data. You are analyzing the data. You're figuring out what are the opportunities to save money for the customer or make the customer's customer experience a lot more smoother. And that's an opportunity. And this is about building that opportunity page.
So when we are building the opportunity, as I said, we are looking back in time. Yeah. So let's say we go back to the job example where we could not pull the data for a specific cycle. Since the opportunity gets regenerated with the latest data, it will be worth to actually go back and say, you know what, we missed an hour worth of data last 4 days. Is it going to make a difference to the real time operations? Probably no. But it still makes sense for us to go back and fill the data so the opportunities are much more accurate.
So in such cases, you would want that failure to react then saying that this is going to be consumed by an opportunities page and go back and fetch it. And that is why you are particular about having this in place. What would have happened otherwise?
If it is a real time operation, so at that point of time, let's say our goal is actually to say, okay, is an application ailing? Do we need to fix something? Now, to figure out whether the problem is still happening, you're looking at the real time data again and again. So maybe you missed like 10 minutes worth of data, but you got newer set of data. You don't care too much at that point because you're not going to make much of an insight from that last 10 minutes because you got newer data. You know that application is still ailing. You need to do something on top of it.
So basically, you have the older data and the newer data. And the newer data tells you a later story. Why care too much about the older one? And that's why you were particular about getting this architecture in place.
That is correct, yeah.
That is one thing that this architecture, the last architecture, could not.
Because it made the decision and it moved on at that point.
Is there another scenario that you could think of where this would be very useful?
This can be extended into other areas too. So, for example, notification failures. Probably not super critical, but customer wants like to get updates about what Sedai has been operating. Was it seeing certain patterns? So, if a notification fails at this point, of course, not as critical as a real time activity, but you still get a chance to say that, hey, you know what, there was a problem with the integration. Your email wasn't configured correctly or your Slack integration wasn't working. Got fixed, go retry. You can reattempt all those things in this architecture. So the actual implementation really doesn't need to actually implement that fault tolerance. The system is handling it for it.
Now, about back to the hub and spoke, right? So I know you rely on your message queues and your failures look into these metrics, these sensors very carefully, and that's how you figure out what to do. Now, at scale, right? When put under pressure, what breaks first, and how does this architecture help you survive?
As you can imagine, if you put more messages into the queue, of course, your infrastructure should be set up in such a way that it can handle it. Of course, so we expect that kind of a disruption happening at the message layer. So, to your question, probably that is one layer we expect to have failures at scale. But the way we have designed it, we have other layers of resiliency. Of course, we have observability baked into every layer, so we could see where exactly the bottlenecks are happening, so that whatever the system needs to act on, that's clearly visible or
I see.
rather automated. But at the same time, of course, these infrastructure, even with all the automations and notifications or rules in place, there could still be failures. There could be loss of data. That is where the multi-layer system comes into picture. So you fail at one level, there could be resiliency built in to actually reattempt the failure or cover the failures. But at the end of the day, it's the goals
The goals are known to the workers as well, correct?
on a need to know basis. So some smaller components. The mothership might have the big picture, but the individual jobs have their own targets.
Got it. And they all add up to the main goal. And now an operational question. So you had this V1, which is the non-hub and spoke model, uh, and the V2, which was built probably a year ago. They both run in parallel. Both were probably operating on the same data, trying to fetch the same thing, and you were testing everything because it's a mission critical system at the end of the day. So you don't want your architecture change to affect that system. So I understand why you ran both together. My question more is like, when you ran both together, how did you make sure that it is not adding a lot of work to validate and replace things?
So this was more of an operational, setup that we did. So of course, apart from the standard software release process, the build and test, we wanted to make sure that when we transition into the new phase, we have the data collected. So what we tried to build was a more of a statistical analysis tool. So we had these two systems collecting data at the same time. And what we did was we created a tool which could do a statistical evaluation of the quality of the data from these two systems. So one fundamental change would be the timing. V1, of course, since the responsibility is different, the way the sequence in which the data is collected might be different in these two systems. So there was no way for us to actually just go compare each metric one by one and say, what, is it going to be exactly the same? Probably not. So it was more of a functional testing. So for example, if we take a very simple example, take a lambda that we are monitoring and we are looking at the metrics of the lambda. Compare multiple statistics of the same metric for the same resource to say, is it matching over time? Is the max of a particular metric matching in both cases?
So you look at the stuff from an automated sensor standpoint. You look at the aggregation. You look at all the properties from it, and then figure out if it's doing its job or not.
That is correct.
The other one would be a lot more work.
Absolutely. Yeah, we will get most of the times we were expecting to get a false positive. So there was no way for us to actually do an apples to apples comparison. Just go to each metric data point to see if
That's
it is
going to be
matching.
hard.
That is super hard, and probably not the right way to do it as well.
It is not. It is not, obviously. Especially with the API rate limiting and all. Maybe the first thing running fine is the reason why the second one failed.
Especially for the metrics collection part, there is also this aspect we need to consider about monitoring providers. So for example, if you're looking at a Prometheus query, it uses its own liberty to actually sample the data at certain points. So it is quite possible that there could be slight difference in
Which
the
is
data.
okay. Which doesn't mean that the system is wrong. So otherwise you would be unnecessarily looking at failures and debugging those. Okay, got it. You have built something in Sedai or used something in Sedai called gig worker and gig
Manager.
Tell us, what exactly does it mean? What did you learn from it?
So as you can expect from the name, it's more like the same gig work that we are talking about. So what the distributed system that we have built right now is actually an evaluation of what we tried with the gig manager, gig worker concept. So this is more bringing in mainstream at this point. So the concept there was, as you can expect, we had a central system listing out a bunch of jobs that it needs to complete. So there was a central registry, and the gig workers registered themselves and said, okay, I can take up these kind of works. And it queried the manager to say, is there a work that I can do?
So it's almost like a pull.
It's a pull. Yeah. With this new system, we've established a proper orchestration layer. And the concept for gig manager was we didn't want to actually restrict it to any specific cloud. We wanted to utilize Lambda wherever possible, Kubernetes, or whichever system.
You could use whatever technology.
Correct. Yeah. Again, as I said, we have gone in. We have tied it down a little bit because we wanted to have observability. The gig manager was slightly open, but conceptually is exactly an evolution. Whatever we have done right now is an evolution of what the gig
This
manager
is almost formalizing gig manager and gig worker. Okay, got it. So in the new design, workers get a job and they execute. They don't manage their schedule, right? What did it take to strip that out and make sure that the other services or the services that have been doing that for years, they're still happy, and you could rip that out and build this into place?
With the previous approach, each individual components knew what to do. In the sense, if there is a failure, if there is a delay, the exporters themselves knew what the backup plan is. A lot of times what happened was it decided, okay, I'm not able to actually get this metrics for this particular resource after X number of retries. So there is a failure, so I'm going to skip and move forward. So the decision was in that system. Sometimes the algorithms or the services which are actually taking action on top of it didn't have the clue. It had to actually implicitly assume that, okay, there is a different system taking care of it. For whatever reason, it couldn't do it. But there was no way for these core algorithms to actually go back and say that, what, no, this is super critical. You cannot miss it. Even if it is like 4 hours late, I want to get the data at that particular point of time because there is a decision making pending on that one. By moving that responsibility to a central orchestrator, now it's much more easier. The dependent service can easily say that, hey, you know what, you missed this one for whatever reason. Now go back and fetch it. I'm actually running a new algorithm, or I'm relearning my reporting to see how it goes. And that particular missing data point, I know you failed X number of times, but I want the system to actually go collect it. Sometimes even a human also can intervene. So, for example, our integrations were broken in an irrecoverable state. The system couldn't do anything. Maybe it was an expired credentials because of which system couldn't collect, and it tried everything and then it gave
It
up.
still failed.
It's still failing. But let's say we got it fixed in another 4 hours. We have a way for the system now to actually go and submit and say that go collect the data at that point of time. So we have more means, we have more recovery options with the new system, because the individual exporters which used to take that responsibility, because the decision was with them till what point it makes sense to attempt to retry. Right now it's brought outside. These individual exporters, they are like, okay, I'm given an assignment. There is a job which tells you exactly what needs to be done. Just go do it. It doesn't need to care about whether it was like in the last 30 minutes or if the data was for the last 4 hours or even last week.
Now that we have that in place, right, let's talk about what does this mean for the engineering teams, right? When you have, I know since AI is discussed heavily now, you had also a hidden agenda here, right? So you wanted to make sure that AI tools are very effective in Sedai, and that was one of the goals. Tell me, how is it related?
AI definitely seems to work better with greenfield projects. So that is something that we have observed. Of course, absolutely AI is like super capable. Given the context, it can do wonders. But keeping it small, keeping the context small, I think is super effective.
Clean and small and complete.
Complete. And of course, there is also the cost angle too, right? The more tokens that you're using, you have a bigger context. Even if you are supplying the context, when you're dealing with a bigger project, AI needs to do more work.
A lot more work, and there are a lot of there could be potentially a lot more mistakes.
Yes, the accuracy is much, much more better when you're dealing with smaller projects. When the context is clean, small, you are getting much cleaner results, more trustable results. So that is one of the reasons why I wanted to break it down further and keep a clean separation of concerns and an established contract, so that these individual systems can be developed faster, validated, and even releases. That is also one of the things. As I mentioned, release management was one of the key aspects that we kept in mind. We didn't want to actually create too much of a drift. If you're trying to fast track certain modules, in the meantime, you end up breaking more contracts than what you like. With this system, with AI, we are thinking that we'll be able to actually mitigate all those problems, because we have smaller projects, cleaner results, and we're putting process in place so that these contracts are well established and taken care. And with AI systems, we can easily make sure that these contracts are met.
I'm sure you've used almost all the code gen systems out there. Do you have a favorite? Second, how should one leader see this as an opportunity and as a careful opportunity, and also as a thing to watch out for when you start adopting AI? Is it just on the dev side? Is it on QA side or testing side, or is it on the integration side, or is it on the unit testing side? Where can one deploy it peacefully, or where should one start deploying AI, and what are the results?
So going back to your first question, yes, we have tried out most of the popular code gen tools, and our team favorite is Cloud at this point. We use it in multiple areas. Of course, development is one area we use. So one aspect that we have always noticed is now people are spending more time designing, reviewing the code, than actually doing the actual work itself. But at the same time, we are using it for other areas too. We are using AI heavily for building the unit test cases, the plan for it, and we have integration systems, simulation systems. So if you see the kind of integrations that we deal with, the cloud provider, the monitoring provider, they are not cheap systems to actually just leave it running in the labs. So we have a lot of simulation systems also backing or simulating these infrastructure layer, the metrics layer. So we are trying to utilize AI everywhere.
Again, about reliability, people think of it as at least two different ways. One, I will think of every possible failure scenario. I'll write code, and this is a perfect code for my production. It takes a lot of time, and in many cases, you will never get to think about everything before deploying it to production. Production is there will be clear impedance mismatches that you have never seen. So that's one way to design it. The second way to design it is it's okay to fail, which is your philosophy. It's okay to fail. It's just that you need to know what your reliability is. And this is about tolerating failures gracefully, right? It's not like a shock. A failure is not a shock to the system. It's a usual thing. I'm just saying an okay thing, and I know how to react to it. Tell me, what is the cost of having this as the philosophy, and what is the advantage of having this as a philosophy?
Going back to your first point, you can try to build a super robust system, trying to analyze all possibilities in the world and try to design a system for it.
It's going to take time.
Of course, it is going to take time, almost impractical in my opinion. And even if you do, there is the new one that just pops up. So if you take that as your approach, it's a never ending system. You will just be on it, redesigning or fixing the system or integrating new cases into the system. And at the end, you are dealing with a super complex code that is like super hard to maintain. And making changes, it will make the system super brittle as well. On the other hand, let's accept the reality. We are dealing with a lot of systems which are out of your control. There are only certain aspects that you can control. Like for example, if you're only dealing with applications that are managed by your own teams, of course you can go back to each individual teams and try to enforce all the stricter rules. That is not what we are dealing with. We are dealing with systems which are managed by totally different companies.
So you do SaaS and non-SaaS.
Correct.
Okay.
Failures are just bound to happen.
Tell me the scale that you guys have. So that is it large companies or very large companies or extremely large companies?
Yeah, we deal with enterprises. We got a lot of enterprise customers. Of course, we deal with small business, and we have variety of customers. So to your point, I think most of these concerns come from bigger companies dealing with bigger systems at scale. Yes.
The same problem at scale and same problem with a smaller set of data is very different, is what essentially you're saying.
Correct. But even with a smaller company, let's say, a small Kubernetes cluster, you're still dealing with the same kind of failures that can happen in an enterprise to it. So your system is actually not going to differentiate too much whether you're dealing with an enterprise level system or a smaller one. The same connectivity problems, like for example, the rate limiting.
It's similar. Maybe rate limiting would happen a lot more with an enterprise than a smaller company, but yes, it's going to
It's
be
possible, yes.
perfect. So thank you so much, Hari, for walking us through your design philosophy. And what I understood is you can design a system that takes a failure as a shock or something unexpected. Or you can design a system that takes a failure as, yes, I know this and I know what to do with this. The difference is, one, of course, handling that failure gracefully. Second would be there are multiple opportunities to react gracefully back then, right? So you could either regress the data in the cases where you miss a data point. You could probably use some regression and fill that data point and qualify it, saying that it's my data point that I've filled in, and move on. Since you're at that point, you could probably say that, you know what, it's going to be consumed by an autonomous system, and say, you know what, I want to go back and try again. Since you're expecting that failure. If you have a system that's not expecting that failure, you don't have these two paths now because that time is gone. So basically you're saying, as if you have something that's mission critical, it's important to design a system that's expecting this failure by design. It can take a qualitative action based on what it's saying and then move forward. Thank you so much. That was an awesome session. And of course, we had our fun times back at school. This is a fun journey with you again.